All right, welcome back, folks. So today we're going to continue with our lecture on image sensors, and then we'll start on the next topic, which is image processing. We finished up with dynamic range last time, but actually I'm just going to rewind to the beginning just to reorient ourselves. I'm going to blitz through the slides that I went through last time just to remind you of the topics that I covered. Okay, so why study robotics, computer vision, mapping from satellite imagery, mapping on the ground, consumer imaging, VR, huge number of application image sensors, obviously. Started with photon capture, photoelectric effect, how we use them in CCDs, CMOS sensors, CMOS being the most common these days. I described the three-dimensional architecture of a CMOS pixel or a typical CMOS pixel, quantum efficiency. We talked about color architecture with color filter arrays in front of the image sensors and how that produces color. Okay, so we got through these topics, some alternative architectures for color that are not as common. The color filter array in front of the image sensor pixels being the most common thing. And then we ended up at dynamic range. Okay, so as a whirlwind recap of things we described last time. And I described demosaicing last time, so I won't take the time to do it again here today. But basically, the high-level problem is to take the array of mosaic values, color mosaic values, that is one per pixel, and then figure out how to compute an algorithm, in other words, to get RGB at every color pixel. Okay, so that's the demosaicing process. Okay, dynamic range. So digital sensors, both CCD and CMOS, as sensors at each pixel, you can think of the response function as being like, okay, light comes to the pixel and some kind of charge is going to accumulate there. And when we digitize it out, we're going to get some kind of digital number. What does that response function look like? And the good news is that it's very linear, okay? For the photoelectric effect in silicon, where the charge is being collected in these photon wells, in CMOS in particular, the response function is very linear, as you can see here. So here's a graph of like a function of the illumination level on the bottom scale here, increasing in a linear fashion. The response in terms of thousands of electrons that are knocked loose and captured is, as you can see, a very linear function, okay? But there may be some nonlinearity, which is very significant to consider engineering-wise, close to 0 pixel value and near the pixel saturation value, okay? So those are some issues that we're gonna talk about, those really important engineering details. But in the typical usage range of that pixel between saturation, max value, and 0, very low light, in the middle, it's very linear, which is great news. And this picture shows the saturation effect, okay? So again, as light increases, light density, photons per micron, square micron here. Square micron is pretty close to proportional to the size of a typical pixel in a CMOS sensor. As the light level increases on the horizontal axis, the signal in terms of electrons that are captured at the pixel is also increasing linearly until there's this breaking point here, as you can see, okay? And then you get a saturated value, which is after that light intensity. At brighter intensities, nothing happens to change the pixel value. It's saturated, okay? The pixel can't hold any more electrons. It's maxed out, all right? There's a difference in these two levels because of the size of the pixel. So in this case, the blue curve represents a larger image sensor. And if it's got the same resolution, then this would mean that the pixel size is larger. Okay, so just think of the blue curve as having a larger CMOS pixel. It is increasing in number of electrons more quickly because it has a larger area over which this light is causing the photoelectric effect to happen. And it saturates at a higher level too, compared to the red pixel. Okay, so the exact rate of increase of photoelectric effect and the max saturation value will be a function of the specific pixel at hand. Okay, what does saturation look like in photos? It's something we've all seen in our photography. It corresponds to parts of the picture that are blown out, saturated, maxed out. They look very white, or as if there's been too much light there. Okay, so for example, here's a picture at normal exposure. maybe some of the pixels up here in the sky, the brightest part of the sky, are approaching saturation. But if we had a picture that was overexposed, say because the shutter was set too long, as one example, we talked about shutter durations and exposure levels when we talked about camera design and lens design. But let's say it was overexposed. In this picture, there's a lot of blown out pixels. So if I go back and look at this histogram, this is a histogram of the pixel intensities, okay, as in this photo. In the blown out case, a lot of the pixels have been shifted to the high values, and there's a lot that are at the max value here, and they're completely white in the picture. Okay, so that's what blown out looks like. And there's a question here, is this related to the triode and saturation regions of MOSFET region of operation? No, or maybe I should say some of those terms are not that familiar to me since I'm not a semiconductor person, but the effect is a little bit easier to understand for pixels than that. So remember in the architecture of a 3D pixel, let me just go back to that picture for a moment to remind you what it looks like. This is a three-dimensional physical structure, right? And the exposed part here of the silicon surface called the photodiode is where the photoelectric effect is happening. And then there's a physical structure in here that's set off with semiconductor processing to create electric field locally to pin those electrons inside a potential well. This is a real 3D structure, so you can't fill it with an arbitrary number of electrons, right? They're gonna max out there in the number that this region can hold because the electric field due to the electrons will start to rise as that happens, right? The charge will increase and magnetic forces will increase, that kind of a thing. So the finite number in here is the thing that eventually is mostly the thing that dominates or causes the max pixel value in the saturation curve to occur. Okay, so that's the way to think about it. Okay, so again, this is blown out pixels. The dynamic range in the real world is actually huge, okay? You might remember, you might have a taste of this in thinking back to radiometry. We talked in their case about sort of the typical light levels, and I gave some tables in there for like things like, oh, what's the radiance coming from directly from the sun or from like a sunlit cloud, to like a book that you're reading in the sun or inside under a dim light, under moonlight, right? All of these conditions are things in which one may want to take pictures. So the dynamic range of this is really large in the world. Even in a single scene, in this case, the interior of a church with stained glass windows that are allowing sunlit, stained glass to shine through, the dynamic range can be huge. So exposure, again, if you recall, one of the measures of it can be in stops. One stop of light, as a reminder from the camera lecture, one stop is a doubling of the amount of light. Okay, so this is a sequence of photos I'm going to show you where taken by Paul Debevec that increases, or actually I'm going to go first to a very dark. Okay, it starts at negative 8 stops. So this is 2 to the 8 times less light. So 1 over 256, the exposure level. And then all the way through to plus 6 stops, okay? If you go to negative 8 stops, you can notice there's a lot of detail in the stained glass window that's lit by the sun directly. So this is in a very, very low exposure situation. You can see that detail of the brightest parts of the scene. If you go to the very, very longest exposure, this is 14 stops. I don't know what 2 to the 14 is off the top of my head, but it's a lot brighter, okay? In terms of the light arriving at the sensor pixels. You can see there's a lot of detail even in this part of the shadow regions of the church, right, that are actually quite difficult to see at a base resolution. So there's a huge amount of detail from very dark to very bright portions of this image. Here is a sequence of images that systematically goes from negative 8 stops through to plus 6 stops. And you can see a doubling or 1 stop increase each step. And you can see that the detail at different levels can be brought out at every light level. There's a way to take all of this information and convert it through to what's called a high dynamic range image. This is a very systematic way of creating a high dynamic range image that creates a linear radiance map that doesn't saturate. Okay, so it just takes it out to the very brightest value that's in there. And this is a way to sort of visualize that kind of a data and to render different kinds of images from that raw high dynamic range image representation. You can, of course, saturate it or take that high dynamic range image and simulate it as if you're shooting it at very short exposure times or very long exposure times. You can also perform certain, as you can see, kind of like a rendering visualizations or effects on top of it. Let me show you a couple of examples. If you take a regular 8-bit image and you synthesize using, say, graphics technique, say like a ray tracing technique, you try to simulate as if there was motion blur, the camera was moving from side to side as you took the shot. You get a certain motion blur in it. I think you can all agree there's motion blur here. But if you think about it a little bit, the motion blur on this stained glass window can't be accurate because you saw how bright it is, right? You got a feel for how intensely bright this is lit by the sun directly versus the shadow regions. So a real photo taken in this scene and moved with motion blur would look like this, okay? There's so much light there that even when it's motion blurred, it would still all be saturated. So having a high dynamic range image that doesn't saturate at the 8-bit max value of 56, but has orders of magnitude more precision at the top end, can allow you to have the raw intensity information from which to synthesize in motion blur these very, very bright pixels blurring out with full saturation. You can do it in a less systematic way and still get most of the benefits. This is a bit of like do-it-yourself HDR. Okay, so you could take 2 shots, one at an exposure that is correct for these houses on the right-hand side that's lit. You could take another one that is correctly lit for the houses on the left-hand side, so you can see that detail. These are, you might notice, kind of blown out now. It's much harder to see the detail, especially in this white painted building. And then you could sort of Photoshop it. Okay, in this scene, it's not difficult to imagine how you do that. You can put them both there and then sort of just keep the pixels that are on the left, keep the pixels that are on the right in the brighter image, and voila, you have a do-it-yourself HDR image. So right away, you can understand the key concepts of the problem of taking a high dynamic range image, in this case, two photos at different intensity levels, and then figuring out how to show it on a display. The displays that you and I look at are typically not very high dynamic range. Even the ones that are called high dynamic range are not going to be able to show you something with the intensity of the sun versus something that's, like in the darkness of deep shade or deep shadow. So displays inherently are finite dynamic range or low dynamic range. And if you have a high dynamic range photo, then the process of compressing it to that display resolution is something that you have to accomplish, with some decisions like we just looked at here. Of course, there's HDR mode on smartphones now. In fact, this is a very old slide when we used to be able to manually say, I want HDR or not. These days, whether you like it or not, all cameras or smartphones are basically taking HDR images and figuring out how to keep the brightest parts and keep the darkest parts in a way that it thinks will be pleasing to look at, to show on the low dynamic range display of the phone. I want to also give you a sense that there's a lot of work in computational imaging to try to look at different ways to capture high dynamic range. In your typical smartphone, I'll come back to and talk about this towards the end of the lecture when I talk about sensor noise. But the typical way this is done is that when you press the button on the camera, it takes a sequence of pictures very quickly at different shutter durations, different exposure levels, and then it combines all of them. But it has to take them at different levels. So you may have taken some pictures of the smartphone where things are moving a little bit if it's brightly lit, and you may notice some weird artifacts because it's taking sequential pictures and combining them. Another way that folks have proposed more at the image sensor level, in this case by a professor called Sri Nayar, who's one of the really tall figures in research speaking wise in our community, our research community, is something that's a little bit more like the color mosaicing architecture I showed you before. The proposal is to have like little darkening filters in front of the sensor pixels. You can see the pattern. Okay, so this one is no darkening filter. And then this one's got one that's a little bit darker, much darker, and then quite dark, maybe one stop each time. Okay, so spanning 4 stops of exposure duration or 4 exposure light levels. And then the goal would be, if you took this one picture, right, you get this funny raw data set, kind of like the funny color mosaicing data set I showed you earlier, where neighboring pixels would have these totally different brightnesses. So you couldn't show it as a photo directly. Rather, you'd have to take this image where each 2x2 set of pixels has one pixel that's at, a very dark to a very bright exposure level, and then figure out how to combine all of them. You could rearrange the image to start to recognize that all the images in every 2x2 bucket, the top leftmost images would be really dark. The bottom, image in that 2x2 pack would be really bright, and so on. So you can rearrange it into 4 images of 1/4 resolution each that have these different intensities, and then say, okay, how do I combine all of these kind of with like the HDR techniques I've described before to make one image that has, decent exposure levels at every pixel. There's also many approaches that have been taken because HDR, high dynamic range, is a really important goal and figure of merit for image sensors or computational imaging systems such as smartphones these days. A lot of different methods have been proposed to incorporate it into the circuit design of image sensors. Many approaches have been tried. I'll mention a few keywords: well adjusting, multiple capture, but triggered at a very fast rate on the sensor surface in the sensor logic. You could measure the time to saturation for every pixel by sort of sampling in time very rapidly within the circuitry of the sensor pixels themselves. You could have pixels that sort of fill up in their photon well depth logarithmically instead of linearly. You could try to design it to have that property. You could have local adaptation on the image sensor surface so that if it's brighter in some cases, those areas fill up more slowly as it notes that's happening. And there's multiple capture approaches at the sensor level as well that require having multiple high-speed, non-destructive reads of the pixel's value during exposure. All of these things can be implemented in semiconductor designs and have been, but they're not very common, it turns out. None of these have made its way through to high volume production in image sensors that you or I use in like the sensors that are in our consumer devices. And the reasons are, even though these are very clever ideas and work in principle, getting them optimized to have competitive performance with the kinds of techniques that we, or the kinds of sensors we have in cameras today has proven to be pretty difficult, okay? But this gives you a sense of the kind of design space engineering-wise for HDR. Okay, I had some questions last time, and I see one again today from when I refreshed this picture of the 3D structure of the pixel and showed the microlenses. Do microlenses straighten light rays out to be normal with the pixel sites? Someone asks today, David does. I'm going to talk about that now, or get into it in terms of pixel structure and micro-optics. Okay, so first, let me give you sort of a bird's eye view into what the sensor looks like as it's sort of laid out. Okay, so I'm going to show you how this sort of builds up in the layers of the sensor surface as it's being fabricated as a cartoon to give you a sense of the typical kind of layers and processing elements that are present in a typical CMOS sensor. So we're going to do a patch of sensor that has 4x4 pixels. Okay, so the first thing is creation of the photodiodes themselves. In this case, for this pixel design, you can see that the photodiodes, this is the part that is going to undergo the photoelectric effect, right, when we expose it, is not the full area, right? They're sort of gappy. In this case, it's about a 50% fill factor, meaning that the photoactive area is about half, okay, of the full area of the chip. The pixel pitch describes the center to center spacing between pixels or edge to edge of this way. So this is a few microns. Okay, in your smartphone today, it might be 1.4 microns, 1.5 microns is a pretty typical kind of a number. Then there's some layers here, polysilicon and vias. These are sort of laying out some of the communication architecture, the wiring architecture for the chip. Here's more layers, metal 1, metal 2. These all combine to provide, again, this sort of selectability of for readout for each of these pixels and to relay that amplified signal off the chip to where we can convert it through to things that we can store into files. Metal 3, metal 4. So one thing you notice is that there's a lot of buildup of these layers of circuitry on top of the part that's photosensitive. So if you start thinking about this, you might already start to note and thinking back to your work on ray tracing or thinking back to your knowledge from camera design, the light needs to flow right optically through to the photosensitive part. So you might notice a bit of a problem here that we've built up in a stacking volumetric sense, a whole bunch of structure that's going to block light from getting to the photosensitive part. So now we have a bit of a tunnel. Can you see that each of these things is the photosensitive parts at the bottom of sort of like a metal tunnel? That's kind of a problem from a photon capture perspective. It's a bit of a practical challenge, optical challenge to get the light to where it needs to go. We'll come back to that in a second. Let's keep building up. Okay, this is a typical place for the color filter array to appear. You can see the RGGB structure that we talked about earlier or last lecture. Okay, and let me see, do I have a picture? Oh, I'll come back to it later. And then on top of this is where micro lenses would go. Unfortunately, this particular cartoon sequence lacks that, but the micro lenses would go on top here, okay? Before I talk about the micro lenses on the next slide, the comment I want to make is about pixel fill factor. So there's a fraction of each pixel that integrates the incoming light. In the previous example, the photosensitive part, that photodiode was a 50% fill factor. That meant that the photosensitive part was 50% of the total area of the chip, right? A simple observation here. At any sort of semiconductor technology level that has to do with the minimum size of the wires and the transistors that can be etched into those chips, right? Which is, of course, for semiconductors, something that in the history of semiconductors is something that's kept getting smaller and smaller, enabling us to have bigger memories and faster processors, as an example, with more transistors. Anyway, at any specific technology level, the wires are a particular size, will need to be a particular size for this CMOS sensor. And then there's a choice for the sensor designers. You can choose big pixels or you can choose smaller pixels. Since the wires are the same size, you can see how in this simple cartoon here, if you choose smaller pixels, the photosensitive part, the photodiode area portion, is going to go down as a fraction of the area of the chip because you need to devote more of it to wiring and circuitry and transistors. Okay, can you see that? So the fraction of the pixel area that integrates incoming light is going to be smaller. The photosensitive area will be smaller for smaller pixels, and conversely, they'll be larger for bigger pixels. The pixel size tends to be much smaller in smartphone cameras because the overall pixel is smaller, a sensor is smaller to fit inside your smartphone, your thin smartphone device. In standalone cameras where it's a bigger box, right, with a bigger area available for the sensor chip, they tend to have bigger pixel areas, so the higher photodiode fraction. Okay. Now, as I showed you a couple of slides ago, here's a cross-sectional electron microscope picture to go with this. Let me orient you to this picture here. Okay, so this is the photodiode area. This is a cross-section of a CMOS chip here. This is the photodiode area where photoelectric effect will happen. Here are these metal layers stacked up here, as you can see. Here's the color filter array that I showed you. There's a few more layers here. There's an oxidation pass layer. These serve different sort of functional purposes to protect the chip, to isolate them chemically from one another. I'm actually not sure what all of these specific parts are, but what's key is that the photodiode is at the bottom of this pretty big tunnel now. And so as to the question that's asked, do the microlenses straighten light rays out to be normal with the pixel size? Sort of, yes, but I think a more accurate or intuitive way to think about it is the microlens is here to take light that's coming, from the main lens. It's arriving at this surface down here, which is the top of the sensor, and then focus it down into the photodiode area to try to avoid these metal layers. If it wasn't there and the light wasn't bent, then a big portion of the light would then just flow straight through and parts of it would just get terminated or blocked by these metal layers and wouldn't arrive at the photodiode. So microlenses can provide a way to increase the effective light collection area of the chip. Here's a picture of it. So here the rays come in, they get bent by a microlens to curve in towards the photosensitive portion and avoid the metal layers, okay? It turns out designing these has a lot of subtlety to it and is actually a pretty high precision task, and a lot of work has gone into optimizing this over years and years of sensor fabrication. So as one of the topics that comes up, for example, here's a schematic of a high-end camera. This is for a Leica M9, which is a pretty fancy high-end camera. Here's a schematic of the back portion of the lens and a drawing of some of the rays that converge to the sensor, which is a pretty large object relative to the back of the lens, right? And shows that, if you're a pixel at the center of the lens, at the center of the sensor, then the rays of light that arrive to you are geometrically centered. And so you want to take this blue set of rays, which is symmetric, and put it through a microlens to arrive at the sensor surface, at the photodiode portion. And the microlens, it makes sense for it to be centered directly over the pixel. But if you look at a pixel that's off near the corner of the chip, it's not quite that way anymore, because the rays of light that are arriving there arrive at these oblique angles, as you can see, right? Because it's not centered along the optical axis. So if you sort of figure the optical design out, you want the lens to actually be displaced a little bit upward in this case to catch this total set of red rays and direct them more optimally towards the center of that photodiode area. And this is actually done in the sensor design of this chip. So these microlenses are not centered directly over the microlenses. The microlenses are not centered directly over the pixels, but they're actually sort of at a slightly different geometric scale. They're slightly, smaller in this case. Okay, so they're slightly compressed, but a very, very tiny amount. But that tiny amount of scaling has a very big micro-optical effect, okay? You might also note that this depends on the design of this, of this lens, unfortunately, and exactly where it's going to be situated relative to the sensor. So there's kind of a lot of different macro-optical as well as micro-optical techniques or engineering issues to be figured out at the same time. Let me tell you a bit more about microlens sort of function and sort of some of the effects that happen that cause problems. So when you want the light to flow through the microlenses, through color filters, down through the tunnel to the photodiode surface, you're trying to get light to bend through a pretty complicated geometry at the end of the day, and a lot of things can kind of go wrong. Here are some examples. If you have light that comes in from a very steep angle, maybe you have a lens with a very wide aperture that is attached pretty close to the sensor surface. So that light, some of the light at least, is arriving at a large angle compared to the optical axis here. It may go through the microlens and get bent, but some of these rays may get bent and still hit the metal parts, get reflected off, and be lost. Others, this is more problematic one over here, it may bend, but it may actually go through the color filter array that's here, red, but actually go over the top of this metal stack and end up in the next photodiode. This is called optical crosstalk of the color information. So what should have gone through a red filter to arrive at a red photodiode, so to speak, is going through and getting added up to a green photodiode. That's kind of a problem. One way to try to mitigate this is to use semiconductor engineering to shrink the depth of this, make the wire layers shorter, put a bigger microlens on it to bend the light more, effectively towards the photodiode. So these are some techniques that sort of happen. What does it look like? If you have crosstalk, you kind of have one color channel that's going into the information for another color channel, like red is mixing into green or blue incorrectly and vice versa. So it's going to tend to wash the colors out. It's going to tend to average them out towards a neutral color, towards a gray color. So if you look at this picture here, you can kind of tell that, or you might be able to perceive that it's kind of a washed out, desaturated color, and this is due to pixel crosstalk. Okay. Got a couple questions. Why not widen the block? I didn't fully understand what block means in this question, so please feel free to clarify, Ray. And Drew asks, is that why there is chromatic aberration? This process that I described here does have a chromatic component to it, obviously, and the microlens array actually is undergoing chromatic aberration too. But chromatic aberration, as we talked about it in the lens lecture at a high level scale, is really more at the macro picture level and not at the micro optical level of these microlenses here. Okay, now let me tell you about the main technology that's evolved to try to eliminate some of these geometric structure issues that I talked about. The structure that I showed you is sometimes called front side illuminated pixel structure. What this means is that the silicon surface on which in a semiconductor fab, you have the wafer, which is a silicon, the surface. And then on top of that is added on these metal layers, right, through a masking and buildup process. So that's the way that fabrication happens normally inside a CMOS, in a CMOS manufacturing process. That's why you end up with this metal effect and the color filter array distanced away from the photodiode. That's called front-side illumination or typical manufacturing approach. Because of this problem of the photodiode being far away and things like optical crosstalk as problems that emerge, there's a so-called backside illumination sensor fabrication process that has emerged and is in very high volume production these days. Not all sensors are made this way, but increasingly they are. So let me tell you how this works. You have the silicon surface, the wafer, okay? This is like, remember, wafers are large, objects, maybe even up to a foot diameter. The metal layers are built up onto it, typical CMOS process. Then what's happened is that the sensor, one part is not written here. The chip is then, the wafer is then flipped over, okay, and mounted. What's not shown here is that there's another wafer. You can take another silicon wafer as a supportive surface. It's flipped over and then glued onto that other surface. That's really easier said than done when it's such a large object. It took many years of experimentation and fab optimization to make this work correctly. But now, once you've flipped it over, what's happened? The metal layers are underneath the photodiode. The problem is the wafer, the original wafer is still on top. The wafer is quite thick, many hundreds of microns thick. So then you can grind it down. So using mechanical processes, the silicon wafer is actually abraded, sandpaper down, if you will. I mean, sort of glorified sandpaper down until the distance that's remaining of silicon before the photodiode is tiny, like a few microns. This is really hard to do over a large wafer where each of these pixels is only 1.4 microns and not have grinding artifacts, grinding problems that cause the quality of this chip to degrade, but it's been optimized now. Okay, after all of this, what's happened? You have the photodiode at the top above the metal layers. Then you could add a color filter array and a micro lens on top of that and arrive at much lower optical crosstalk, hopefully, and a superior kind of process. Okay, so this is FSI, diode at the bottom, BSI, backside illuminate with the photodiode on top. So this is a pretty common thing these days. And the majority of CMOS sensors, not all, are BSI today in smartphones, some cameras, things like that. Why don't we place the silicon on the top at the very first time, but instead we flip it? Oh, great question. It's just because in all CMOS labs, in all CMOS fabs, you start with the wafer and then you have to put it on a surface and then you spin coat photoresist on, you mask it, you expose it to light with a mask, you etch it away, and then you put metal on top. The only place you can do that process is on the top surface of the chip from a mechanical standpoint, right? Access standpoint. So you have to build the metal layers up on top of the silicon surface. And the silicon surface is where the photodiode happens, where a photoelectric effect will happen. So you have to build up all of that circuitry, which you need for readout. And then if you want the silicon to be at the top again, that's why we have to flip it over and then back grind it. Okay, so it's a very complicated mechanical process, conceptually simple, but very complicated. And yet they went through all of the effort and years to optimize that because it can really make a big difference in, as this slide says, in quantum efficiency and lower crosstalk, as I shared earlier. Okay, the next topic I want to talk about is pixel aliasing and anti-aliasing. So think again of this fill factor, right? It's a fraction of the area of the pixel that is actually integrating light. I showed you this example when we talked about aliasing and anti-aliasing. Do you remember this example? I said, oh, something's going wrong in the image on the right-hand side. What happens exactly? It's a simulation of pixels with 25% fill factor, where I made the picture on the right by just taking 1 out of every 2 by 2 pixels on the left-hand side. So for every 2 by 2 block of pixels on the left, I just kept 1 of the pixels and put it on the right. If you do that, you end up with tremendous aliasing problems, okay? And this is a really important problem, practical problem in image sensor design. So where are the sources of aliasing? There's the finite fill factor. Only a finite portion of the sensor is actually integrating light. But even if it wasn't for that, think about the color filter array, right? We are masking out red, green, and blue in this pattern. If we think about just the red, we're actually only sampling red once out of every 2x2 pixels. So this looks very much like this subsampling procedure that I described over here, right? So there's a lot of subsampling that's happening potentially, and anti-aliasing, aliasing that's occurring because of this insufficient sampling rate. And so we know from our theory look in sampling and anti-aliasing that once aliasing is in there, it's very difficult, if not impossible, to remove it. So we have to anti-alias this somehow. And anti-aliasing was what the prescription for anti-aliasing in a general sense was to filter out the high frequencies before we sample, right? Filter out high frequencies above the Nyquist rate before we sample. Okay, so how would we do that? The one way to improve the fill factor is things like microlenses. So if only a portion of the silicon surface is actually photosensitive, we could put a microlens array on top of that, which will take the light over the entire area of the pixel and concentrate it into the photosensitive part. So that will make the full area sensitive. That will help to blur out the signal better, to not have it just be aliased to a subportion of the pixel area. But what about this color filter array? This is a really terrible subsampling, pattern here. It's so important. It's such a terrible subsampling pattern, and so important that technology has been developed optically on the sensor surface to solve this problem, to anti-alias this. It's called an anti-aliasing filter. An optical low-pass anti-aliasing filter is the name often given to it. And it uses a very specific technique, which I'm going to tell you, optically speaking, and a very specific material to accomplish it. So let me first tell you exactly what it does, and then we could try to interpret it from an anti-aliasing perspective. What's used is a layer, actually 2 layers of a birefringent material. So a birefringent material is one that has the optical effect shown in this picture here. Calcite is an example of such a material that exhibits birefringence. What you can see here is a piece of paper. It's got calcite printed on it. There's a crystal of calcite that's sitting on top of that piece of paper. And what you'll notice, if you look carefully, is that the word calcite is duplicated. Okay, can you see that? Actually, if you look carefully relative to the line of the text, you can tell that it's duplicated and it's been shifted. One is shifted up to the left and one and down to the right. That's the nature of calcite, is that, and birefringent materials in general, is that they take a ray of light that enters that material and they split that ray into 2, is the unique property, okay? You can see a picture of it here schematically. So each ray of light that comes in will get split at the entry point into the material into 2 parts and exit as 2 rays, actually, right? So calcite word enters once to the crystal and exits as 2 calcite words. Okay, so that's what happens. And what's used is 2 layers of this, very, very thin layers of this material, rotated at 90 degrees so that in sequence, a ray of light enters, gets split in 2, and then each of those rays gets split in 2 in the orthogonal direction. So it exits this optical low pass filter layer. Each ray exits as 4, okay, in a 2x2 pattern. And the thicknesses of this low pass filter crystals are exactly machined so that the exit distance, the gap here, is exactly the same as a pixel spacing. Okay, so the ray that would have gone to 1 pixel is replicated into 4 exit rays, optically speaking, and those 4 rays of light will go to a 2x2 array of pixels. That's what's going on in this optical low pass filter, okay? Yeah, so someone asked a great question. She asked, but this is not exactly removing high frequencies, right? It's more increasing a sampling rate. Yeah, it's a bit of a head scratcher the first time you look at this. And I think it's a great example of trying to interpret how certain systems have an effect on, well, what effect they're having on the signal that they're recording, okay? It turns out that this is an optical low pass filter. It is a it is a low pass filter. in a signal processing sense, it is knocking out high frequencies. The way to understand that is that it gets replicated across 4 pixels, but each pixel is integrating over a block of like an area, a finite area. Okay, so you have to think of it at the scale of the entire pixel. Each of these rays is then, let me see if I can explain this properly. The collection of rays that would have arrived at 1 pixel and been integrated into its 1 pixel value is now split into each of them individually, of course, but as a collective, they're split into 4 sets, each of which is going to put the same light that would have gone into 1 pixel and been integrated into 1 digital value. It's now going to add into all 4 of the neighbors in a 2x2 block as well. And the way to interpret that is that now the filter that's incorporated is 2x2 times wider, where before we were integrating over the area of 1 pixel. That was the low pass filter that was available to us. Not enough. Now with the anti-aliasing filter here, it's doubled up. Okay, so we're integrating over a pixel area that's 2x2 as large. And because we're sampling in this color filter array in the worst case by a 2x2 subsampling, that's a good amount of high frequency and knockout to match this subsampling pattern that's here. Okay, let's take a look at some pictures for what this effect this has. So without an anti-aliasing filter on the left-hand side, wait, let me make sure I got that right. Yeah, on the left-hand side without anti-aliasing, you can see that there's more detail. Okay, right? Remember when we talked about aliasing and anti-aliasing, we said that if you put in a low-pass filter to avoid aliasing, you should expect to lose frequencies, which lose detail, but you'll avoid things like moire, you'll avoid things like, aliasing artifacts like jaggies and things like that. So on the left-hand side, you can see there's more detail that's lost in the image on the right-hand side. But if you can look in the bottom left here, you can see things like aliasing artifacts like color moire. Can you see in this like very close white lines here? There's some false pink and false green in this picture that's a lot more diminished on the right-hand side. I think I have some more examples. Oh yeah, here. Okay, so here's an example. If you just take a picture of like clothing, this is without the anti-aliasing filter. The very fine threads in this silk pattern here actually are a very high frequency pattern that are problematic for a real stress test for aliasing. And you can see it manifested as this blue and yellow moire pattern. If you can see it, if I can point it out here. And with the anti-aliasing filter, it's greatly diminished, okay? Now, we talked about aliasing and anti-aliasing in practical systems is never absolute. It's always sort of a trade-off. So, but you can see it's greatly diminished with the anti-aliasing filter here. How does this differ, question, how does this differ from taking an image without a low-pass filter and then just doing a 2x2 box blur in post-processing? Brian asked, great question. So this takes us way back to our second lecture, maybe third, I forget, on the anti-aliasing lecture. So very, very fundamental question. So I'm glad you asked, so I get to reiterate this. Anti-aliasing is something where you have to filter out the high frequencies before you sample. You cannot sample and then filter out the high frequencies, which would be what Brian is describing here, saying, why don't we just take the picture without the anti-aliasing filter and then just solve the problem in software, just blur it afterwards. You can't filter then sample is not the same as sample then filter in this anti-aliasing sense. And I don't have the picture here to remind you, but if you go back to the anti-aliasing lecture, I show a specific example of that. Okay, so if you create a picture with jaggies, rasterization wise, if you make a picture of jaggies and then you try to blur it, you just end up with blurry jaggies. Okay, unfortunately, that would, if we could do that, it would make a lot of engineering systems a lot simpler to implement. Okay, last topic, a big topic for image sensors has to do with noise. Okay, so what's image noise? When we take photos, we note that they have some kind of graininess to them, especially if we take them in low light. For example, if you take a picture like this, you might zoom in on it a little bit and say, oh, look, in the part of the picture where, you know, the fireworks are, I sort of look at it and I notice this sort of graininess here, right? It's a variation between dark and bright intensities. And it's generally worse in low light situations, shadows of images, things like that is something that you'll notice in your photography. Where does it come from? Okay, it has to do with signal to noise, which is a property of real engineered systems that have to measure real quantities, right, and with physical devices. And it comes down to what is the signal to noise ratio. If we have a very high signal compared to noise ratio, then the signal will dominate and the noise, the graininess will be hard to see in our pictures. If we have a low SNR ratio, then the graininess will be a lot more apparent. Okay, so the SNR is just the average pixel value for that intensity portion of the image divided by the standard deviation of the pixel value at that location, or sigma for mean divided by mu for mean divided by sigma for standard deviation. And there's a formula here for SNR in the dB scale, 20 times log base 10 of this ratio of sigma over, of mu over sigma. So as an example, in the dB scale, which is very common out there, so if SNR improves from 100 to 1 to 200 to 1, then in the dB scale, it improves by 20 times log base 10 of 200 minus 20 times log base 10 of 100, which is 6 dB SNR improvement, okay? Okay, so that's some of the basics on the numeric scale. What are the sources of noise? If you only remember one thing from this portion of this lecture on image image noise, remember this part, okay? The most fundamental source of noise in images or imaging systems in general that we can never get away from, no matter how great our engineering is, the fundamental part is called photon shot noise. And that has to do with the fact that the number of photons that arrive during a photographic exposure is a random variable. It will vary from exposure to exposure of exactly the same scene. And it will vary from pixel to neighboring pixel, even if the scene is completely uniform in intensity. And the reason why is that the number of photons which is a finite number and a countable number, the number of photons that arrives at that pixel on the sensor and is converted to by the photoelectric effect, that number of photons is a random number that's governed by the Poisson random distribution, okay? You can think of it as, the Poisson distribution is a very, very general statistical, statistical phenomenon. You can think of it like the number of raindrops that would fall on a patch of pavement. Like, what is the number of raindrops that occur in a thunderstorm at any moment in time? It's a random number. If we counted it over 1 second and then over the next second and then over the next second, it's going to be a slightly different number of raindrops, even if the intensity of the rain remains constant, of course. Of course, because the number of the raindrops are falling in a random Poisson process as well. So what's the Poisson distribution? It's the probability that a certain number of random events will occur during an interval of time. It's not just for photon counts on image sensors. It's for all kinds of things that you can model, all kinds of things that you want to count, right, in the real world. The probability that a certain number of actual events will occur, if you know the mean rate, the average rate, and if each of the events is independent, then it's given by the Poisson distribution. And the Poisson distribution has a derived equation. You can derive from first principles, statistical principles. And so if on average lambda events occur in the interval of time that we care about, the probability P that exactly K events will occur instead of lambda is given by this equation here. So the probability that K occurs, given that lambda is the mean, is equal to lambda to the power of K times e to the negative lambda over K factorial, okay? A somewhat formidable looking expression, but an analytic one that's easy to calculate. Here's what it looks like on the right-hand side, okay? So you can see for lambda equals 1, which means that on average, we expect one event to occur. On a photon count perspective in an image sensor, this would be very, very dark conditions, okay? That would mean that we expect only one photon to arrive at the pixel during the shutter duration. That's not very typical, but lambda equals 1, that's what it represents, okay? So you expect one on average, but sometimes you might even get 2, 3, 4 photons arriving. Lambda equals 4 is shown here. It's starting to look a little bit more like a bell curve, but has still a bit of a bias to one side. By the time you get to lambda equals 10, you can see the shape of this Poisson distribution here is starting to look very much like a bell curve. And in fact, for any lambda greater than 10, it's very well approximated by normal distribution, okay? Where, that's gonna be the next slide where I talk about that. Okay, so just know that for Poisson distribution, like in photon statistics, the true distribution is given as shown here. For any reasonably large number of expected events or expected photons, it's going to converge on something that's very much like a Gaussian, okay? What is that Gaussian? The Poisson distribution is well modeled by a Gaussian where the mean is, of course, the same. So the mu, the mean of the Gaussian is equal to lambda, the expected number of events. And the variance is also equal to the expected number of events. Okay, so let me say that again. The Poisson distribution, once it's a reasonably large number, say lambda over 10, it's very well approximated by a normal distribution where the mean and the variance are equal to the expected number of events. Okay, the standard deviation is going to be given by sigma equals the square root of the variance. So sigma is equal to the square root of the mean number of events. So the error grows slower than the mean, which means that in an SNR sense, which remember again is sigma divided by the standard deviation, the mean divided by the standard deviation, the SNR is going to get better and better in this case, the higher the number of photons that we expect to capture. Okay, so back to photon shot noise SNR. If the photons arrive in a Poisson distribution where the mean and the sigma are as I described, the SNR is equal to the ratio between these two things is equal to the square root of the expected number of photons. So as the expected number of photons increases, that means the exposure duration is increasing. The signal to noise ratio is also increasing. Which is a really good thing. Okay, so the brighter the light level, the better the SNR. Okay, some examples. Let's say that we had a pixel. Let's say the pixel collected 10,000 photoelectrons versus 1,000. Okay, so two pictures. One it collected 10,000. The other picture collected 1,000. The first picture would have an SNR improvement that is very significant. It's going to be equal to the SNR improvement of square root of 10. Okay. The ratio between these two and then the square root, so square root of 10 better, or plus 10 dB of SNR improvement, which is very significant. Here's another example. If we open the aperture in a camera by 1 f-stop, which is a doubling of the light, that will increase the number of photons by 2x, so the SNR is going to increase by a square root of 2. Okay, following from this SNR equation up here, or plus 3 dB. Okay, so again, if you only remember one thing about image sensor noise, that would be the thing to remember. That's the fundamental, cannot get away from it source of noise. And as engineers or image sensor engineers, we strive to engineer devices that in the situations in which we use them, the noise due to the device is very small compared to the shot noise. Those would be called shot noise limited devices. And once you're shot noise limited, you cannot make a better device for that imaging situation. Now, this is very hard to do in general. It's hard to build devices of that kind of quality. And in general, image devices inject a lot of spurious sources of noise of their own that pollute the image of their own. Okay, so let me give you sort of a sense of what some of these look like. These change all the time as technology improves, but pixel noise is often due to something called dark current. As the device, the image CMOS sensor, for example, is operating, electrons are just randomly dislodged inside the structure of the device due to random thermal activity. Those free electrons will get captured by the photo wells, and they're going to pollute the image value that we get for each pixel. Dark current will increase with exposure time. So if you take a long picture, then this source of noise will be larger. It also increases with temperature. So if you're shooting in hotter conditions, or if your device heats up as it's operating, which is really common for CMOS sensors, then that will also increase this dark current. It varies from sensor to sensor and includes its own shot noise. Okay, so the dark current itself is a random process and will carry Poisson statistics. There are hot pixels that are very common in image sensors. This is just because when you try to fabricate a device like a CMOS sensor that has millions of pixels that each have lots of transistors in them, lots of micro wiring around them, each has its own color filter array, microlens array. Bad things happen. Bits of dust arrive on it. Fabrication errors occur that will lead to bad pixels. Okay, the pixels may have features like electrons leaking into the well due to manufacturing effects. There may be just be dead pixels. Some may be stuck on so that they amplify to an unnatural degree. They can change over time, and every camera has bad pixels. To give you sort of a sense, this is maybe 5 or 10 years old at this point, but at that point, an A-class sensor, which was maybe like an 8 megapixel sensor with at an A class would have be allowed to have up to 8,000 bad pixels in them. Okay, so this is a pretty common problem. Let's see what else I have here. Okay, so some ways to sort of lower dark current or hot pixels are to cool them. So this is like some typical numbers for a pretty an older cell phone camera sensor at this point. But a lot of these stats are pretty hard to come by for current devices. But this is from a cell phone that was typical from a few years back. One thing you could do to achieve better performance on dark currents and hot pixels is to chill the sensor and achieve much lower dark current, as you can see here. You could also take 2 pictures. You could take a picture of the scene that you care about, and then you could keep the shutter closed and take another picture in the dark and use that as a real-time sort of estimate of the dark current in order to try to subtract it from the image that you just took. So both of these techniques are pretty common in different imaging applications. There's also fixed pattern noise. The architecture of any one of these CMOS sensors has rows and columns and not just wires that are associated with them, but sometimes amplifiers on the edge of the chip that are used to amplify the signal near to those columns and rows. Those will show up as structure because of manufacturing variation in those edge amplifiers, or due to the properties of the wires themselves are transporting. So you can see sometimes some vertical and horizontal structure that's related to this. This can be characterized. You could read it once and then factor it out in the image processing of these pixel values from this chip. There's also read noise. This is very typical and fundamental to CMOS sensors. It's thermal noise in the readout circuitry. So when you reset the pixel to 0, the value that it's set to will have some variation to it, right? Because you're resetting the charge level in that pixel to some kind of baseline level, but it will never hit exactly that baseline level the same for every pixel. So that will inject a bit of noise into the readout value after you take an exposure and read from it again before resetting again. So there are various techniques that have been designed in order to try to minimize this effect, but read noise is a very typical characteristic of image sensor noise. Okay, that gives you sort of a whirlwind tour of some things that happen on the sensor surface. More practical to the computer science side of things is the phenomena that happen when you get the picture itself. So I want to talk about some of this and show you pictures associated with this. What's the effect of downsizing on image noise? You take a picture with your camera, the one in your pocket, it's probably going to be 8 megapixel, 12 megapixel, some might be 20 megapixel. When you view it on your phone, the display on your phone is probably 3 megapixels, if that, maybe less than 3 megapixels, okay? So there's going to be some image reduction even from taking it and then viewing it the first time on your phone. And of course, when you transmit it over the web, people will look at it at different resolutions in different formats later. So what is the effect of downsizing on image noise? The effect is that it's going to denoise if we average spatially. So this is taking a picture here and then just zooming all the way into individual pixels and noting that in this case, there is a significant amount of noise that you can see from pixel to pixel. This is the noise in an SNR sense at the pixel layer. If we average it by going to a lower resolution, as you can see here, instead of a zoom in on the lips, but a slightly zoomed out version or a very zoomed out version here, you can see that this grain structure has disappeared. It goes down here and it's almost invisible in this original image. And the reason for that is that if we average over a large number of these pixels to arrive at 1 pixel in the original viewed image, then the SNR is going to increase. It's almost as if we get the statistics of this area of image pixels, not just one individual image pixel. But, oh, I think I have a sequence here, 2 pictures to compare. We could compare that against, averaging over a large set of pixels there versus picking one. Okay, if we just pick one of these pixels instead and put it as a representative into the output picture, then we would retain the image statistics and the low SNR of the full resolution image. Okay, so this is point sampled in that sense, and this is averaged down. And averaging down, as you can see, has a huge effect on improving SNR. Someone asks, is this partially why people get fancy 8K cameras to shoot 4K footage? It's a good question. That one actually has a little bit more of a complicated answer. So the high level answer that I'll give here, the simplistic answer is no, actually not in that case. But the reason why 8K for shooting 4K has a bunch of different sort of characteristics that are interesting. In interest of time, come talk to me about it in office hours if you're interested, and I'd be happy to go through all of it. Okay, I want to return to this topic of averaging, but for using multiple pictures. So just as you saw that averaging neighboring pixels helps noise, if we average multiple pictures, that's going to help as well. So here's a single frame taken in a dark room. This is quite old, as you can tell, using an iPhone 4. Okay, so going back quite a bit, but this is a useful example because you can see the structure of this noise very clearly. If you took 30 pictures with that exact same camera system, but later aligned all of them and averaged them together using appropriate image processing, you can see that the amount of noise can be greatly reduced. This was actually a first generation prototype of something developed by Mark Lavoie. At the time, he called it SynthCam, that he developed much more at Google when he went to lead the Gcam team there that was responsible for a lot of the innovative image processing that went into the Pixel camera phones that eventually came to be known as I'm sort of run out of energy today. What's the name of that algorithm? Anyway, that was incorporated into Pixel camera phones. I'll try to remember. HDR plus. Thank you very much, Apik. Okay, so the SNR increases as the square root of the number of frames here if it was photon shot limited, so neglecting read noise, which will actually sum, but not average out. Okay, all right. That is our whirlwind tour, or concludes our whirlwind tour of image sensors. And to see if I missed any leftover questions in the chat. No, I think we got through all of them. Okay, great. We will do most of image processing next time, but we have some good time remaining, 15, 20 minutes or so. So I want to start us on that. There you go. Here it is. And actually, we'll start with a really interesting case study. One of the most interesting topics in image processing that has to do with JPEG processing. So this will work out great. Okay, image processing. There's my chat window. Here it is. Okay, so let's start lecture 22 on image processing. A shout out to my buddy, good buddy, Kayvon Fadalian, who created the majority of these lecture slides. I tried to upgrade a few of the pictures a little bit at least. Okay, here we go. Let's start with a case study. When we think about image processing, let's start with talking about JPEG compression. How does JPEG compression work? There's lots of other image compression formats out there, ones that have increasing utility today or penetration in the market today. But JPEG is still an extremely common image format out there, probably still the dominant one in a lot of ways. So how does JPEG compression work? The other reason why it's really great to talk about is that there's some really big ideas in here that even if JPEG becomes obsolete, these big ideas will persist. Hey, Rishi, can you help me to check where the non-muted background noise is coming from and help to mute that? Thanks, Rishi. Okay, so what are the big ideas in JPEG? Number one, low frequency content is, from a frequency content perspective, low frequencies are predominant in images of the real world, not high frequencies. I'm going to come back and show you some examples of that. Number two, the human visual system is less sensitive to detail in chromaticity than in luminance. If you remember from color lecture, chromaticity has to do with like color of the rainbow, which color of the rainbow is it, and how saturated is it. Luminance is how bright is the picture. Is it dark? Is it bright, close to white, close to black? The human visual system is also less sensitive to high frequency sources of error than low frequency sources. Okay. Therefore, taking those two big ideas, image compression of natural images can reduce the perceived error in the images by localizing the compression error into high frequencies and into chromaticity. Okay. These are some of the big ideas, the biggest ideas in JPEG compression that I want to work through with you. Okay, so let's start by looking at this issue of chromaticity versus luminance, because it's so beautiful, I think, visually to look at it and develop the intuition for it. JPEG does its compression in a space, color space called Y prime CBCR. Okay. This is a perceptually motivated color space. Remember, a color space is just a mathematical representation for colors in 3 numbers. Y prime CBCR is a perceptually motivated color space that's got a lot of similarities to the CIE lab or L star, A star, B star color space that I walked through in some detail with you last time. In this Y prime CBCR space, Y prime is luma, which is very similar to luminance or lightness. CB and CR are chroma channels. They're along a blue-yellow axis and a red-green axis, as different from gray. And they're very similar to A star and B star in sort of flavor, although the mathematics underlying them is a little bit different, okay? But if you took this color RGB image here and you broke it, this is what Y prime, CB, and CR might sort of look like if we break it up and try to visualize the individual channels. Here's an example image, okay? Some staircase, okay? In actually a pretty famous hotel in Malaysia called the Blue Hotel. The thing I want to show you is, okay, if you look at only the Y prime, this is the luminance channel. Is it light? Is it dark? This is full resolution. If I downsampled it, okay, and I'm going to downsample it quite extremely here. This is a 4x4 downsampling. So every 16 block of pixels, 4x4 block of pixels averaged down to 1. I've averaged that and then displayed it here. So this is a pretty severe downsampling. And as you can tell, it's highly visible, right? We can clearly see the degradation in detail. Now let's look at what happens in the chromaticity, okay? This would be the CBCR channels. This is a visualization of that CBCR channel information at full resolution and then at downsampled CBCR resolution. So again, here it's downsampled 4x4. This might be a little bit harder to see. So I'll go back and forth. This is full resolution CBCR. This is downsampled 4x4. If you stare really closely at the details, you can probably perceive some of these differences, maybe here and over here. But now let's try to put them together a little bit, okay? Let's take an example of where we take the original image and we compress in Y prime channel, in the Luma channel. What do I mean by this? I mean compression in this very crude sense of taking the original image and then just downsampling, so just decreasing the resolution. So we're storing fewer pixels, right? We're storing 16 times fewer pixels here. Let's do the compression in Y prime, but keep the chroma full resolution, okay? You can tell that this picture is terrible, okay? You can totally tell that there's huge jaggies here and loss of detail everywhere, okay? But let's now do the opposite. So let's put the compression into CBCR. So let's keep the Y prime channel at full resolution and then use the downsampled CBCR channel, 4x4 downsample. That's 16 times reduction there. And it's a lot harder to tell, if there's anything wrong. In fact, if I put it side by side with the original image, it's actually really, really hard to tell if you stare very closely, you'll probably notice some color pixel shifts in the regions over here. But the luminance structure of the image now is providing, centering your visual system on the detail. And the color information, even though it's low resolution, not very high detail, is plenty to fill in very convincingly all the color information that's present here. And exactly as Ray says, yeah, the takeaway is that downsampling the colors or putting the compression error into colors is way more effective for image representation than putting compression error into the luma. So that's exactly what JPEG does, okay? JPEG uses chroma subsampling in Y prime CBCR space. So that's a couple of different variants of how much compression it uses, okay? Those are sometimes called technically 422 or 420 compression formats in JPEG. The 422 representation works like this, okay? It returns 2/3 of the original pixel values. It stores Y prime at full resolution. And then it stores the CB and CR at half resolution by squashing it horizontally. Okay, can you see what happened there? So the CB channel, which should have been as wide as this one, got like squashed in half, okay, to keep only half the resolution, and similar for the CR. So if you total this up, you can sort of see that if originally we had 3 times these number of pixel values, now we have all of these and then half of each of these. So that's where we get 2/3. Okay, of the original data. 420 is an even more, aggressive compression. We retain only half the total original pixel values. We store Y prime at full resolution, and we store CBCR at half resolution. Okay, 2x2 subsampling. So it's not like the picture I showed you before. I just tried to show you a really dramatic example so you could see how strong and effective it is. I did 4x4 subsampling for you, okay, in either Luma or CBCR. Okay, so that's big idea number 2 that I described originally. Okay, put the compression into luma or luminance rather than chroma or chromaticity, which are equivalent, at least for our purposes technically for today. The other idea I said was that the human visual system is less sensitive to compression error or image error that's in high frequencies as opposed to low frequencies. So to get into frequency space, we can use our friend, the Fourier transform that we studied earlier in aliasing and anti-aliasing, but we use something that's very, very close. Mathematically speaking, we use, instead of a Fourier transform, we use a discrete cosine transform. So not a discrete Fourier transform, but a discrete cosine transform, which still puts it into something that is organized in frequency. So these are the basis functions, well, written here mathematically speaking. Just as Fourier basis was in sinusoids that we talked about of increasing frequency, same here, except we use cosines. And so it's all real valued. And in particular, and it's also 2D basis functions because we're using it for image compression. So both in the I horizontal direction and J vertical direction. These are the basis functions for an 8x8 block of pixels. If we put it into a discrete cosine transform, then this would be the 64 basis functions for representing an 8x8 block of image values in DCT coefficients. What does this mean? It just means that we take a block of 8x8 pixels and we're going to represent it by a weighted, linearly weighted combination of these basis functions. Okay, and what do these basis functions look like? We got low frequency here, right? Constant value. We got low frequency, sort of one sinusoid or half a sinusoid in horizontal and vertical directions. And then as we increase, it gets higher and higher frequency horizontally, higher frequency vertically, and then cross products of that to where in the bottom here, it's the full checkerboard high frequency pattern. Very similar to 2D Fourier transforms that we looked at before. So how does JPEG use this? It transforms, it takes an image, breaks it up into 8x8 blocks of pixels. Each of the 8x8 blocks of pixels, it transforms it into the DCT space. And then it prioritizes keeping the low frequencies in the DCT. How does it do that? It takes the original 8x8 patch, takes its projection onto these basis functions. Let's say then you get these coefficients, okay? These are the weighted values that we multiply these basis functions by and add them all up in order to arrive at the original 8x8 block of pixel values. So these are just the coefficients for those basis functions. Then we use a quantization matrix. This quantization matrix is how JPEG prioritizes low frequencies. Okay, so we take these values and we divide them element by element by this matrix here. You'll observe that this matrix, which by the way, any JPEG implementer is free to pick any values they want inside this quantization matrix. But to prioritize low frequencies, you divide by smaller numbers for low frequency values and larger numbers for high frequency values. This is occurring in, it turns out I mean, you could do it in floating point and then round as well, but this is occurring in fixed point arithmetic, okay, fixed point integer arithmetic. So after you do these divisions, these small values in the DCT coefficients divided by high values in this quantization matrix result in a lot of zero values, okay? Averaged out to zero values in integer fixed point math. And so you wipe out a lot of the values, which provides a lot of compression already. Then the quantization is going to quantize these values here. And the quantization of zero values is very efficient, so that provides a lot of compression efficiency. By the way, this matrix here and the specific values in it are something that's changed by the image quality level that you may have seen if you ever choose a compression level or image quality level when you compress an image into JPEG. Quality 9 just means that the quantization matrix has smaller values. And if you have a very low quality value, then these quantization matrix values will increase, okay, create more zeros here. That will, of course, also increase compression error. So what do compression artifacts look like? If you choose a low quality value, as I said, then you end up with a lot more zeros, and the 8x8 block of pixels that you get from that approximation is going to have more error in it. And so if you note here in this very low quality compression, there you can see the boundaries between these 8x8 pixel blocks pretty clearly. In this medium quality one, it's a lot harder to tell because the representation of those 8x8 blocks of pixels is a lot more accurate, and therefore the boundaries to its neighbors is a lot less. Even in the low quality case, though, regions of space that are very smooth, it's much harder to see this error there, okay? Let me skip over this one point here. JPEG is not very good for representing very high. It's designed for natural images like photographs. It wasn't really designed for text, and it performs substandard for text where there's very large jumps between black and white values, for example. Okay, so what else happens? We take the quantized DCT values, multiply the basis functions. The last step in encoding this is more for an information perspective. So what happens in the rest of JPEG? We do an entropy encoding. This part is lossless. We reorder all the values that we're gonna enumerate these quantized DCT values in. The ordering is shown here. Why? Because it goes from low frequencies to higher frequency values in a linear ordering. And then we run length encode, which means that we just sort of say, here's a value that's different. And then here's how many repeats of that value. These are all pretty unique at the beginning, so the run length encoding is not that efficient. But once we hit a very large patch of zeros, like over here, it'll just say, oh, here's a zero value, and there's going to be like, I don't know, 26 repeats of this, okay? So the very large number of zeros is very efficient from a run length encoding perspective. And then finally, something called a Huffman encoding is used to compress the non-zero values and obtain maximum compression efficiency. Okay, so JPEG compression summary. We convert the image to Y prime CBCR, downsample CBCR quite a lot, either to half or 1/4 the original size. For each color channel, Y prime, CB, and CR, we take each 8x8 block of values. We compute the DCT. We quantize the results by prioritizing keeping the low frequency values and knocking out the high frequency values. We reorder the values, run length encode it, especially the zero spans, and then Huffman encode the non-zero values. Okay, so that's a summary of what happens. The theme, though, so to return to the first slide that I had about this, it's about exploiting perception in visual computing. It's a larger way to think about what's going on in this example of JPEG compression. So JPEG is an example of the general theme of exploiting characteristics of the human perceptual system to build efficient visual computing systems. So we're perceptually insensitive to color errors. I showed you, this blue hotel photograph to try to convince you of that. So that's why we separate luminance from chrominance in the color representation. JPEG specifically chooses Y prime CBCR, and then we compress chrominance. We're less perceptually sensitive to high frequency errors. So we use this frequency-based encoding and a cosine transform to accomplish that. And we compress out high frequency values, trying to drive them to zero. We also perceive lightness non-linearly. That was not actually discussed in this lecture, but we encode each of the pixel values in JPEG non-linearly to match the perceived brightness that we get using something called a gamma curve. Okay, so that's one more example of this general theme, though not one that I described in detail in this particular lecture. All right. Okay, so that's the entry point for image processing lecture, the end of JPEG. We'll continue next time by continuing to talk about basic image processing operations. Okay, so folks, great to see you. Have a good weekend, and we'll pick up from there next week.